Kubernetes has emerged as the most mature platform for managing, configuring, and deploying containers at scale. It provides you a declarative, API-centric way to describe container-based applications that can self-manage, self-heal, self-scale, and much more. Hi everyone, this is Kavya from Edureka. Welcome to today's session on Kubernetes Storage. So in this session, we will explore the impact of expanding the automation and orchestration from applications and networking to also include storage. And you will look at how you can apply these technologies and patterns to your applications. Before we begin this interesting session, let me address the agenda for you. Firstly, we will discuss some of the challenges of data. We will also move ahead and talk about volumes in Kubernetes. We'll discuss persistent volumes in Kubernetes. We will understand why do containers really need storage, and then discuss some of the storage solutions in Kubernetes. Then we'll move ahead and discuss the Kubernetes storage best practices and then conclude the session with a case study. I hope the agenda is very clear. Kindly take up this time to subscribe to us and do not forget to hit that bell icon to never miss an update from the Edureka YouTube channel. Also, to learn more about new trending technologies, visit our page, the link to which is given in the description box below. So, without much ado, let's get started. Challenges of data. Now, containers have changed the way we build, ship, and run applications. This transformative technology affords great velocity and application portability, but has also brought new challenges to technology teams. The challenge of persisting data in a transient system. As I've already mentioned in the introduction, Kubernetes is the leading orchestrator for container workloads. So let's discuss a particular scenario. What if a container stops for one reason or another? Kubernetes is definitely able to start a new instance almost immediately, making availability and recoverability something that happens in seconds as opposed to minutes or even hours. But this new instance of the application may not have access to the file system from the old instance, especially in the case of local file systems, so additional orchestration is required to ensure that the stateful component of the application is bound to the instance at restart. This focus on stateless applications and epithermal systems have prevented certain stateful and complex applications from being a good fit for this revolutionary technology. As companies look to bring applications into Kubernetes, the inability to persist data through a container's lifecycle is undesirable. People need a way of dealing with stateful applications and persisting data, all without inhibiting the positive aspects of the self-healing capabilities of the Kubernetes platform. Now, to get a better sense of how to address challenges in Kubernetes, we'll take a look at one of the earliest challenges that have been successfully addressed, that is handling log data. The Kubernetes community found a successful way to address log data by sending it to an external system. Now, by using solutions such as the Elasticsearch, Logstash, and Kibana stack, you have a pattern of leveraging an agent in a container alongside different applications. Now, the process enables developers to send logs to a standardized endpoint, which makes it portable and flexible. In the enterprise, moving storage into external system isn't something new or unique. The use of a storage area network, that is SAN, has been a staple practice of enterprises for a large number of years, but typically it has been implemented by delivering a pre-configured, dedicated volume to a virtual or physical machine. So now the next question that arises is, how do you provide a stable storage solution for any type of content with an equally composable and portable convention as the EKL pattern? Firstly, you do not want to inhibit your IT team's abilities to back up, recover, or secure the data either. Fortunately, this is where Kubernetes enters the picture. Its features and capabilities address this challenge as they are rapidly growing and maturing. Kubernetes began with the storage features as part of the Pod API and soon expanded these into standalone interfaces, which include volumes, persistent volumes, storage classes, and container storage interface. In the previous sentence, if you noticed, I mentioned the word pod. You must be wondering what pod is, right? A pod is simply the smallest schedulable resource in Kubernetes. It is a logical collection of containers which ensures the encapsulated containers share resources and are hosted on the same node in your cluster. So typically a pod really contains of a single container and is an instance of an application. Now let's move on to the next topic of this session and discuss volumes in Kubernetes. The Kubernetes volume in its simplest form is a directory that's attached to a pod and mounted to one or more containers in the pod. Such coupling is tight and is a foundational construct for how data can be presented to a container. Now, because of this relationship with the pod, Kubernetes volumes are designed to have the same life cycle as the pod. If an epithermal volume is defined by the pod, for example, its contents do not survive a container restart. Now, when a pod is removed from Kubernetes, any volume relationships are broken and epithermal volumes will be destroyed. Kubernetes volumes are typed, which is how you define the storage mechanism backing the volume. Volume characteristics may be defined via volume type specific parameters. This may be a physical disk or path on the Kubernetes node, a SAN, a network attached storage, or even a storage service from a crowd provider, to name a few. So what really volumes do is it really allows applications to have a very defined storage part that stays consistent through the redeployment of a container. Okay, so this layer of abstraction really helps, but on its own does not solve all persistent storage concerns. There are many special volumes available for use, like the empty directory, config map, secret. So all of these have their own advantages and can be used in many ways. When a pod is scheduled to run on a node, a volume is created on that node and will remain there until the pod is deleted or moved to another node. This volume is an empty directory volume that begins empty and is backed by the storage of the host itself. The other two types of config map and secret are volumes whose content is actually stored by Kubernetes. This mechanism is often used to pass configuration information, such as credentials, into a container and ensure they are available wherever the pod is scheduled to run. Now that we understand volumes just allow applications to have a defined storage path that stays completely consistent and same throughout the redeployment of a container, let's move ahead and talk about persistent volumes in Kubernetes. Now, as the relevance and utility of local storage options are literally exhausted, the need arises to leverage external storage. Individual nodes may have storage provided by a SAN, but that's not the same as being able to orchestrate the external storage along with the rest of the instructions for managing an application. Kubernetes here provides a persistent volume claim, which is a request for storage. So the request made by the persistent volume claim defines characteristics of the storage that are desired by your application, such as access and volume modes, size of volume, selectors, storage cache, all of that. In conjunction with PVCs, that is persistent volume claim, Kubernetes also provides a persistent volume resource. Okay, so a persistent volume has historically been a pre-provisioned storage volume, but more commonly is provisioned from a storage class dynamically and made available to the cluster for use by a pod. So persistent volume is simply a piece of storage in the cluster that has been provisioned by an administrator. And it also provides a persistent volume claim, which is basically a request for the storage. And you can see all of this represented in the diagram on the screen. In a Kubernetes cluster, when you create a storage class, you define provisioners, parameters, and reclaim policy. Provisioners are the utility or component responsible for interacting within the backend storage system, whereas parameters helps in the setting or values that you can pass to the provisioner. The reclaim policy instructs Kubernetes to either retain or delete the volume when it's released. If your volume is retained, you may need to perform your own volume cleanup and maintenance. To make storage systems support more extensible, plugin based storage driver mechanisms are really important and necessary. So instead of only developing and shipping storage drivers as part of Kubernetes itself, storage vendors and users wanted a way to provide and use the drivers they need and to omit the ones they do not. So along came CSI and Flex Volume, which are the out of tree extension points for storage drivers. Both of these plugin types allow for administrators to deploy storage drivers that can be loaded dynamically by Kubernetes nodes and both provide the ability to provision volumes of any number of storage types. Flex volume was introduced first, but CSI is emerging as a more dynamic and comprehensive specification. Flex volume is included for completeness, however, the convention is being only deprecated. Only use it if you must. On the other hand, the CSI specification outlines a number of storage operations in a way that can extend to additional container orchestration platforms. Now that we understood what are volumes and persistent volumes in Kubernetes, let's move ahead and talk about why do containers need storage. Okay, so when you think of adopting a new application architecture, such as, cloud native, it seems really logical to do with a new application. More times than not, however, you do not find yourself only developing new applications. If you're like most folks, you have to blend the traditional needs of applications and the functions they serve while applying emerging application architectures to improve speed, adaptability, and costs. Now, at this point, Kubernetes and the real world collide, and storage is a big part of this transformation. So, I'm sure most of you are aware that you build business applications in containers. They implement business logic, automate decisions, and really set out to make our lives much easier. Your applications also produce a lot of data. It may be in the form of files, data tables, reports, and much more. Building small functional bits of logic into containers is a very good decision, but what would you do with so much data? Now, without storing data in a persistent volume, the file system of a container is also epithermal. Now, when a container restarts, the file system is reset to whatever the file system state is in the container's image, and files not stored in a persistent volume do not survive the restart. You really need a sustainable and supportable way to store data and objects in flight or as output from your applications while taking advantage of the portability, scalability, and recoverability of containers. Now, instead of fighting the natural tendency of containers to be stateless and lightweight, the pattern looks to augment Kubernetes to facilitate the behaviors we want. If your Kubernetes cluster has access to or is in public cloud providers such as AWS, you have the platform services that can provide block devices, file system as a service like Elastic File System, databases as a service like Relational Database Service, and object storage like Simple Storage Service. Now, each of these offerings have individual performance characteristics, that is, they have their own pros and cons, and you must align your application and workload with the proper type of storage for its needs. This alignment requires multiple unique methods and processes for orchestrating the various storage mechanisms, and not all are aligned with the way the application is orchestrated by Kubernetes. GCP, AWS, and Azure all have storage drivers in Kubernetes that help offload the concerns of managing and provisioning the platform storage services and provide a common interface in PVCs and storage classes. But how do you achieve parity for clusters running inside corporate data centers or for storage services you wish to use when a consistent experience in Kubernetes doesn't exist yet? There's one solution, which is to host your own storage system. So let's move ahead to the next part of the session and check out the storage solutions in Kubernetes. Hyper-converged infrastructure is the combination of compute, networking, and storage, all implemented as software and all deployed on the same nodes. Now, this software-defined approach introduces immense flexibility in the underlying hardware, eliminating dependency on specific vendors and specialized components. It also affords IT teams the ability to achieve portability and consistency of management and configuration. Rook is a storage orchestration for Kubernetes. It uses the declarative nature of Kubernetes to make storage services self-healing, self-scaling, and managed with similar conventions as your containerized applications. Rook uses a plugin extensible architecture to help you automate storage administrative tasks such as deployment, bootstrapping, configuring, scaling, provisioning, and monitoring. So, what does this really mean? Rook allows you to use a declarative style of management that really empowers you to achieve as code capabilities for a multitude and various types of storage types. It implements the new necessary Kubernetes objects so you have a common interface to provision storage software that provides object, block, and file system storage types. That is, Rook goes way beyond primitive storage types and also really enables you to orchestrate databases and other storage types in a claims-based fashion. This common way of dealing with volumes and now other storage types in Kubernetes is one way it is growing to orchestrate all of the storage types. So Rook on its own isn't a storage system. It must be coupled or collaborated with a portable storage subsystem or service. So Rook has operators to support the following storage backends, and one of it is Ceph. Ceph is a high-performance distributed storage platform designed to bring similar capabilities found in GCP and AWS to any cloud platform such as Kubernetes. It provides object storage, block storage, and distributed file systems backed by a single reliable storage cluster, which is running on commodity server hardware. Ceph is designed to be extremely scalable. It is based on the reliable autonomic distributed object store that is a self-healing system that distributes and replicates data safely across storage nodes. It then layers a distributed file system, block storage service, and S3 compatible object storage service on top of RADOS, that is the reliable autonomic distributed object store. So there's a huge advantage of using Ceph, that is, it is open source and purely software. It can really provide its rich set of storage capabilities and features when deployed across almost any server hardware and either hard drives, SSDs, or any combination of the two. It is widely used in a range of environments, especially private cloud deployments, but it can be complicated to properly provision and connect a Ceph system to Kubernetes. Rook simplifies the deployment and management of Ceph itself and also provides an extremely simple and Kubernetes native way to provision storage services. So some of the storage best practices are with the persistent volume settings, limiting the storage resource consumption, and definitely making requests and limits on the resources. So the persistent volume life cycle is independent of any particular container in the cluster. Persistent volume claims are a request made by a container user or application for a specific type of storage. So when you're creating a persistent volume, you will have to follow its rules. Okay. The next best practice is to limit the storage resource consumption. It is definitely advisable to place limits on the container usage of storage to really reflect the amount of storage actually available in the local data center or even the budget available for cloud storage resources. There are two main ways to limit storage, that is resource quotas and storage classes. The next best practice is to implement resource requests and limits. Kubernetes provides resource requests and resource limits that really help you to manage resource consumption allowed for individual containers in Kubernetes. So a resource limit can be specified for some temporary storage. Okay. So setting storage requests and limits can help prevent containers from being constrained by resource scarcity on container hosts or taking up too many resources unexpectedly. With this, let's move on to the case study. So the case study that we'll be talking about today is by using a cloud provider storage service to externalize data from the container. As you can see in the figure, you can see the implementation of the application and storage patterns in a progressive fashion. You can use each of these application and storage patterns in the HCI system. Okay. You can also see an application that consumes storage via a persistent volume. And if you move from AWS to a different provider such as Google, you can provision the application in the exact same way. However, if you're running Kubernetes on premises, there is no pre-existing storage service to consume. So here in the figure, an application is attached to a persistent volume backed by Amazon EBS. So now what the application can do is they can use a storage provided by Rook, Ceph, or another software-defined storage solution, which is in turn consuming compute and storage resources from any cloud provider. Okay, so it shows your application deployed to a hyper-converged cluster, and the diagram really illustrates your ability to make your applications portable across similar HCI clusters hosted in two different providers. It is really critical to point out that this is accomplished with only one set of orchestrations to manage applications and storage, thanks to the common interfaces and consistency provided by Kubernetes plus the Rook and Ceph combination. You can now move your applications as is between providers now. So the diagram that you see has an application that consumes persistent volumes that are provided by Rook Ceph in any environment. So with this, we come to the end of today's session on Kubernetes storage. I hope you had a great time understanding the nooks and crooks of how Kubernetes storage works and what are the important topics within it. If you have any queries, feel free to leave them in the comment section below and we'll get back to you as soon as possible. Until next time, thank you.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!